who will give us the second talk. So over to you.
Okay, thank you. By the way, I just sent you my this presentation file to Yogesh by email. So I mean, maybe Yogesh can upload the file. Okay, so thank you very much for the invitation, and especially thanks to Professor Matthew Joseph. And today I'll talk about the stochastic reaction-diffusion equations. And basically we'll consider the long-time behavior of stochastic reaction-diffusion equations. And this is based on joint work with Davar Khoshnevisan and Carl Mueller and Shang-Yuan Shiu. Okay, so here is our equation. So we have a heat equation, the diffusion equation, and reaction term, and the noise term. So our spatial space is on torus. So we consider this equation with the periodic boundary condition. And here C is a space-time noise, and lambda is just a fixed constant, and sigma is a globally Lipschitz function. And U0 is, we assume that the non-negative and continuous function. Okay, so in here, if V of U is 0, okay, so no drift term. And if sigma of U is just a U, then this is this equation is called the Parabolic Anders model, which has a lot of attention these days. And we'll consider this model more details later on. And if V of U is like a U minus U square, then this equation is called the stochastic KPP or stochastic Fisher-KPP equation. And if V of U is like U minus U cubed, and this one is called the stochastic Allen-Cahn equation. Okay, so here is our main question. So what are the invariant probability measures of this equation? So if there is an invariant probability measure, how many of them can you have? So we actually started this problem when I was in MSRI in 2015 with Davar and Carl. And then Davar showed us the paper by this Zimmerman et al. So he is the physicist, and actually they show that they show through the simulations that the invariant measures or long-time behavior of this equation depends on the parameter lambda. So in this talk, we'll consider the long-time behavior of this system and how it depends on the parameter lambda mathematically. So let's first look at the Parabolic Anders model. So this is a Parabolic Anders model, and it has a connection to many other models. Like we can consider this one as like particle systems. So particles are moving like Brownian motions on torus, but under the random environment of this C. So this random environment tells the particle to die or to replicate at the rate of this lambda. Then this U of Tx is like a conditional density of particles at time Tnx. And the conditional expectation is with respect to this underlying Brownian motion. And also if in polymer models, like a partition function is like U. And once we take a log of U, then this log of U is called the Hopker solution to KP's equation. And once we take the gradient of log U, then it becomes a stochastic Burgers. And for passive scalar equation, once we take the like a Laplace transform or Fred transform, then we get something like this Parabolic Anders model. Mathematically, so the solution to this can be written as like this way, just like we saw in Muhammad Fundon's talk. And the right-hand side, this stochastic integral is can be understood as or in the sense of Walsh or Dallang, like a generalized Ito sense. And one interesting property from this Parabolic Anders model is that it shows intermittent phenomena. And mathematically, this intermittency, the definition of intermittency was given by Kamona and Molchanov. So they define that, they say that U of Tx is fully intermittent if this gamma of k over k is strictly increasing, where this gamma of k is given by like this way. So these guys called the case moment Lyapunov exponent. But instead of actually looking at checking this gamma of k over k is strictly increasing, we can look at the first moment. So if a gamma of 1 is 0, usually this is easy to check, since if initial data is non-negative, then in fact the solution is also non-negative. So when k is 1, here we can just take the expectation of not the absolute value, but just u of tx. So once we take expectation of u of tx, this stochastic integral part will be 0. So we have only the initial data part, the homogeneous heat equation part, which is non-negative. So you can see easily that this one, gamma of 1 is 0. And also gamma of k is finite. I mean, this is the upper bound, so it's kind of easy to prove this. So the main thing is to see the full intermittency, we have to show the gamma of t is gamma of 2 is strictly positive. By the way, once we have this, then u of tx is in fact fully intermittent. And so for the second moment, so with Davar, we show that actually second moment, actually considered at the fixed time, like expectation of u of tx is like e to the some constant times lambda to the 4 times t. And then Muhammad Fundon and Matthew Joseph, they actually sharpened our results. And also Muhammad Fundon and Noalat, they got the long time behavior of the second moment. So in fact, this parabolic and this model on torus is intermittent. So let me show you the simulations. So this is a simulation of parabolic and this model. And here is initial data is just 1. So let's run the simulation. So because of this space-time wide noise, we have a lot of peaks. And then as time goes on, we see some tall peaks, right? Here, maybe here, like this way. Okay, let's stop here. So this really shows the intermittent phenomena. So there are some tall peaks and small tall peaks and very tall peaks and small, like this way. Okay, so here our question is, what will happen as time t goes to infinity? Okay, so instead of actually parabolic and this model, we can look at the more general equations, so-called the stochastic heat equation. So for simplicity, we assume that the initial data is just 1. And sigma of u is a globally Lipschitz function with this condition. So obviously, when sigma of u is just u, it satisfies this condition, and this condition is called the intermittency condition, introduced by Fundon and Khoshnevisan. And under this condition, the system, this stochastic heat equation is fully intermittent. Okay, so here, if there is no noise, lambda is 0. So since we start from this like one function, the constant function, and we have a periodic boundary condition, actually for all time t, the solution is just 1. On the other hand, if lambda is positive or negative, it doesn't really matter. Since C is also space-time wide noise, which can be positive or negative. But so anyway, as long as lambda is non-zero, then expectation of u is 1, and the second moment grows like e to the some constant times t. So U is a fully intermittent. On the other hand, if we consider the long time behavior of the solution, so with probability 1, so supremum of U of Tx over X, this guy goes 0 like e to the minus constant times lambda square T. So it goes 0 uniformly. So in fact, from this, we can easily get that there is a unique invariant measure, which is just a delta 0. So it has a full measure on this 0 function. So in other words, for parabolic Anderson model, we have a unique invariant measure. Kind of it's a trivial invariant measure, right? Once we start from 0, so U0 is, say, U0 is 0, then since sigma of 0 is 0 here, you can see that. So it'll be just 0 forever. Okay, so in this case, we have the unique invariant measure. So let's look at just some proof. So we have the solution. And so we integrate this one with respect to X. Okay, so
Kunwoo,
now,
just one question.
Yes.
Kunwoo, so in your theorem, this is for the general case, when you also have a V?
Huh?
For that equation, but then a sigma of 0 is 0, isn't it?
Yes, it gotta be a sigma of 0 is 0.
Okay, but then it just remains 0. If you're starting from 0, then you're just...
Yeah, it's just a remaining 0, yes.
Okay. Mm-hmm. So I'm struggling to understand what is the non-triviality of the result, that there cannot be another invariant measure, is it? Or
yes, so
the uniqueness.
Right now we don't have a derivative term.
Right.
Yeah, so once we have a derivative term, so we'll consider the this equation.
Okay, so the theorem is also true with a derivative term.
Yes.
Okay.
It'll depend on lambda. I mean
okay.
Sometimes it goes to 0 or not. Yes. Okay, so let's look at this. So you can just think about this case, lambda times U. Okay, the parabolic Anderson model. So for the proof of this, basically we integrate this one with respect to X. Then here the integral of this with respect to X will be 1. It's a Hicks kernel. So we get like this equation. And this is just a martingale, right? So we use a Ito's formula to get this equation. And then it's on the torus, and so you can actually get the quadratic variation of this martingale is like this way. So kind of simple exercise. So if X is a continuous martingale such that the quadratic variation is like CT, greater than CT, then we get this one. If you think about like say quadratic variation is really equals CT, in other words, xt is a Brownian motion, then we have a reflection principle so that we can get this right away, right? So it's more or less the same thing. We have here, we can use time change of Brownian motion, and then use reflection principle to get this one. So from this, we apply this one to here log mt to get like this way. So probability that the L1 norm, so this one, the total mass, is greater than e to the sum minus constant times s for some s, the probability of this will be really small. So this basically says that the total mass goes to 0 exponentially fast almost surely. But our interest is that L1 norm, L infinity norm, the sum norm. So to control the sum norm, obviously the sum norm is greater than L1 norm times some constant, but we want to control the sum norm by L1 norm. So here is how we do. So here is the Hicks kernel. You can think about just Hicks kernel on R. Then it's bounded above by like 1 over square of t or 1. So for initial data part, so once we bound this one by a 1 over square of t, we can get like this. And if we bound this one by the maximum of u0, we can get this. And then a minimum b is less than a to the epsilon times b to the 1 minus epsilon. So using this one, we can have the following moment estimate. So we can bound the moment by this L infinity norm and L1 norm here. And then using the Kolmogorov continuity theorem, so we can actually put the supremum inside of expectation. And here, now next, we can use just a Markov property. So here we start from 0, but we can start from at time t, and then we look at u of say t plus 2. Okay, so u of t plus 2 will depend on u of t, right? But L infinity norm of u of t, it may be large because of intermittency. But here is epsilon. Epsilon is there, and epsilon is arbitrary. On the other hand, this L1 norm, say of ut, we already know that it will be like exponentially small. So actually, this one can dominate the whole thing. So that we can actually show that the supremum goes to 0 exponentially fast. Okay, so this is for the parabolic Anders model case. So now let's look at the more interesting case, the reaction-diffusion equation. Okay, by the way, any questions? Okay. So now we consider this stochastic reaction-diffusion equation. And V of U is given by like this way. So x minus f of x, f is non-negative, and blah, blah, blah. The point is near, so V of x behaves like x when x is near 0. On the other hand, if x is large, V of x behaves like minus f of x, and f of x is like x to the some power greater than 1. So for example, V of u can be u minus u to the alpha, and alpha can be your favorite number, which is greater than 1. So here in this talk, we can just take V of u is like u minus u square. Or you can take u minus u square plus u cube minus u to the 4, doesn't matter. Okay, and we have a same condition on sigma with the intermittency condition, and sigma of 0 is 0. And assume that u0 is continuous and non-negative. Then there is a unique Milde solution done by Sandra Chorai. And also we can show that the u, in fact, are structurally positive for all time t and x with probability 1. Mueller and Shang, they didn't really work on this reaction-diffusion equation, but you can truncate this one to make global Lipschitz. And then by taking the limit, you can show that it's actually structurally positive. It's not easy, hard. So our question is, what are the invariant probability measures for 3? So here, if lambda is 0, and V of u is like u minus u square, then obviously if u is 0, once it starts from 0, it will be 0 forever. And also 1, then it'll be 1 forever because we don't have noise. But on the other hand, if lambda is a positive, then once we start from a 0 function, it will stay 0 forever since sigma of 0 is 0. So from here, from the equation, I mean, at least we know that there is one invariant measure, which is a delta 0. So what else? I mean, are there other invariant measures? So here's the main theorem. So there exists two constants, lambda 1 and lambda 0, such that if this lambda is like a large, then we have just one invariant measure. which is delta 0. So in this case, in fact, the solution actually, the supremum of u of tx goes to 0 exponentially fast. On the other hand, if lambda is like a small enough, then there exists a unique probability measure mu plus on this set of the non-negative continuous functions, which is invariant and it's singular to this delta 0. It doesn't charge on this 0 function. So basically you have two the extreme measures. So by the organic decomposition theorem, we have infinitely many invariant measures, which are the linear combination or convex combination of these two. And for the measure, this one in fact has a probability measure on this C alpha, so held space with the parameter alpha. And in fact, this one comes from the following the organic theorem. So mu plus is in fact the limit of this guy. And here the convergence holds in the total variation norm. Okay, so the theorem says that basically the number of invariant measures depend on the parameter lambda. And if lambda is large, there's only one invariant measure. And if lambda is small, then there will be many. So we first consider the first case. Okay, so here's the equation. And let's consider this equation. So we know that u is already non-negative here. So if we compare to this the v, this u minus u squared is in fact when u is positive, this one is less than v. So by the comparison principle, in fact, u is less than v. And for v, here we have this drift term, but it's a linear drift. So we can, just by transformation like this, we can get rid of this drift term. So we get this stochastic heat equation. But here sigma, this sigma T of W, but this one has the same Lipschitz constant as the previous sigma. And it satisfies a sigma over here 0 is 0 and so on. So from the previous result on the stochastic heat equation, this guy is less than this number, almost surely. Okay, so now we go back to U. So U is less than V, and V is like this. So take rho and then divide by T, then we can, so this guy is bounded above by this number. So we can see that as long as lambda is large enough, this one goes to 0. So this shows that we have only one invariant measure, just like for Parabolic Anders model. Okay, so now let's consider the more interesting case. So let me recall the main theorem, when the lambda is small. So here, so the second one basically comes from the first one. And the third one comes from the fourth one. Fourth one is comes from basically the first one in the proof. So we'll focus on the proof of the first one. Okay. And for the first one, so we have to show the existence of the non-trivial invariant measure. And then we'll show that the invariant measure, which is singular to delta 0, is unique. Okay, so let's start the proof. So first, the existence of non-trivial invariant probability measures.
Kunwoo, just one question, Kunwoo. Yeah, I just had a question. So your theorem, the main theorem that you stated, not this one, the previous slide.
Mhm.
Yeah, so, but in the parabolic Anderson model, you showed that for all lambda positive, there is only one invariant measure, right?
Yes.
So isn't that sort of it's not saying what the theorem is saying, right?
We have
because for the if here you're saying that when it's below lambda 0, then there are more than one invariant measures.
Yeah, we have infinitely many, yes.
Yeah, but for the parabolic Anderson model, for all lambda positive, you have only one.
Yes, because we have a drift term here.
But f of 0 is so f cannot be identically 0.
No.
I mean, f cannot be u. F cannot be f of u cannot be u.
F cannot be u, right? Yeah.
Okay.
So the condition on F is, you can just think of like this case. Phi of u is like u minus u. Alpha should be greater than 1.
Okay.
Yeah, it can be u to the power 1 point or some, 1.11, but still, yeah. Okay, yeah. So somehow it kind of makes sense already. I wanted to tell you later, but here, like u minus u squared. So if u is very large, then this one is dominant term. So it's actually dominating the kind of parabolic Anderson model case. So we don't have intermittency in this case. So we can really feel the drift. So drift really does something. I mean, here, like without noise, drift does something so that we have two fixed points. So okay, so let me let's talk. Let me give you some proof. Then you'll see why we have at least two exactly two extreme measures. Okay, so now we consider the case where the lambda is small. Okay. So first, we'll show the existence of a non-trivial invariant probability measure. So let's consider the Markov semigroup for U. So P sub t is given by like this way. And since U is Markov and P is the semigroup is Markov, and in fact, we can also show that this is a Feller semigroup. In other words, it sends continuous bounded functions to continuous bounded functions, and also stochastically continuous. So now we can use the classical theorem, so-called the Krylov-Bogoliubov theorem. So if there exists a probability measure nu such that this guy has a tight subsequence, then this has a weak limit, and this weak limit will be an invariant measure. Okay, so we want to show that this sequence is tight in this space. And so we'll work on this u minus u squared case. So as I said before, when u is large, this one is a dominating term. So unlike the parabolic Anderson model, in fact, the moments in C alpha norm over all time t is actually bounded. So this already says that, by Azela-Ascoli, u is actually tight, right? But it just says, only says a tight on the set of non-negative continuous functions. So we'll show the following proposition. Then it shows that once we have this, the number 4, so this says basically that this solution doesn't stay near 0 much time. So it doesn't take charge on 0 function. In fact, we'll show the following thing. So we'll show that the more stronger result. So with probability 1, this solution doesn't stay much time near 0. Okay, so for this existence, this lambda doesn't really matter. I mean, not for this one, lambda doesn't matter. For this one, lambda really matters because of this here minus u square. I mean, near u is 0. okay, if u is close to 0, if lambda is small, okay, then the effect of noise will be small, but we have a positive drift, so that the solution doesn't stay near 0 much time. So to show this claim, we'll use a random walk argument. So we'll define the stopping times and comparison processes such that u is greater than Vn of t when t is between those stopping times. And then we construct from this Vn an asymmetry random walk, which goes up with a higher probability when u is small. So basically what we are trying to do is, if u is here, then we'll somehow construct a Vn, and from Vn we have the random walk, and this random walk has a higher probability to go up, so it doesn't really go down much. So because u is above this random walk, we have this claim. So this is the idea, and so let the LT of H is infimum of H, UT of H is supremum of H, and if u is say small, then u minus u squared, well, the upper bound is always true whenever u is positive. But if u is small, we can compare to this one as like u of 2. And then assume that tau 0 is 0, v0 is 1 over 8. And the reason why we have this one, we compare to this, is we want to compare the original equation to this, the equation for Wn. So this drift term, because of this, so whenever u is small, this drift term is always less than u minus u squared. And then tau n plus 1 will be the smallest t plus tau n, such that the infimum, so the infimum of Wn, so we run this Wn, and once this one goes up to this twice then this the previous initial data, they will stop. Or if this is the Wn is goes up and down, but it goes down by half, then we'll stop. Or if the maximum now goes up to this 4 times from the previous level, then we'll stop. The reason why we have this one is we want to use this condition. We always want to compare this one to this guy. So that's why we assume that the maximum doesn't really go above than 1, okay? 1/2. So if such a t does exist, then we let Vn tau n plus Tx is like Wn. And then now the next one, the initial data for the next one. So in case 1, whenever it's still small enough, then we just take the same level. But for 2 and 3, it's already by half, so it's okay. We can just take this one. But if the maximum goes up to like 4 times from the previous step, then we'll make it reflected to like half of the previous one. And then define x sub n is like log 2 to the like this one. So this xn takes values, so the difference will be like +1 and -1. And let ln is like this way. Okay, then, in fact, as you can see, if tau n is not finite, then it doesn't make sense, right? But in fact, we can show that the tau n is a finite almost surely. And also, so probability that this xn plus 1 is goes up by 1 with a higher probability, greater than 2/3. The reason why we have this is that when lambda is small, the effect of noise is actually small. But we have the drift term, so if u is small, u minus u squared is basically u. It goes up always. So this one actually wins the effect from the noise. So we get like this kind of probability. So since xn plus 1, all stretch go up, so from the random xn plus xn is not exactly the random walk, by the way, but so now we can actually construct another random walk, so that asymmetric random walk, so that we can show the number 5. So once we show this, then now we compare this one to the original the solution. Here L1 upper bar and L1 under bar is just the upper bound of this one and lower bound of this one, which can be constructed as an IID or random variables. And this one is kind of comparable. So once we show that this one is 0 with probability 1, then this one will be 0 with probability 1, which shows our claim here. So this shows the non-trivial invariant probability measure, the existence part. Okay, so now any questions? Okay, so now the uniqueness part. So so this is our equation, while f of u is basically u square. So far we show that if lambda is small enough, then there exists an invariant probability measure which doesn't take this delta zero function. So now our goal is to show that this one is really unique. Okay. So usually to show the uniqueness, usually we show the semi-group is a strong fellow. Strong fellow means it sends the bounded continuous functions to continuous bounded functions. What am I doing? Bounded functions to continuous bounded functions. But it's not really easy to show that this the semi-group is strong fellow, since sigma of u, like if it's sigma of u is u, then u can be very close to 0. So instead, we'll use the coupling argument by Mueller. So here we construct 2 solutions, and then we'll show that they actually are completely coupled in a finite time. So just to explain this coupling argument, we'll just assume that the derivative term is 0. Okay, there's no derivative term. In fact, for this the coupling part, the effect of drift is not much. Okay, so now the question is how do we construct U and V so that they actually couple? So here is the Mueller's construction. So we don't really consider these 2 things in the same, not the same space-time noise. So U follows this parabolic and this model, and V follows this equation, where f is just square root of 1 minimum y, and g of y is square root of 1 minus this square. And C1 and C2 are independent space-time noises. So here, f square plus g square is 1, right? So, and C1 and C2 are independent space-time noises. So in fact, this one itself is a space-time noise. So that's why we call this a pairwise monotone, and also we assume that U0 is greater than or equal to V0 for now, okay? And the difference is small. So that's why we call this a pairwise monotone coupling. And here, so both of them actually has the same distribution as for the parabolic and the model. But here, if U and V, so since U0 is greater than V0, and then, so initially U0 is greater than V0, and if U and V are close to each other, then this F is it's just like a y, so it will be almost very small. And this one will be like a 1. So by the comparison principle, for just a single, actually space-time noise, this one will be bigger than this v. So we have this, the u will be greater than or equal to v. And in fact, once they meet, if u equals v, then this one will be 0. And then we have C1 and C1, same thing. They both driven by the same space-time noise. And once they meet, then initial data at that point is the same thing. So then they will stay forever. They'll stay together forever, right? So we have a completely coupling. Okay, so now, how to show really this complete coupling? So we look at the difference. So let delta of Tx as u minus v, then it's non-negative. We already know that. By the way, for the existence, this one can be, for the existence is okay, but we don't talk about the uniqueness. We don't really need a uniqueness, and okay, so we only need the distribution. So we don't really need a uniqueness, and it's not known, in fact. Okay, so now
just one question. So you said you're using comparison principle for u and v, is it? But
it's
then
not exactly. So intuitively, so if we say u0 is just strictly greater than v0.
Yeah.
Okay, and then they, so u is already here, v is here. But once they are very close to each other, if they are very close to each other, okay?
Yeah, yeah.
Then f will be really small.
Yeah.
F is just a y, right? F is u minus v.
Yeah.
So the effect from this noise is almost, it's 0. Oh, suppose they really meet.
Yeah, then it's
0. Then we have the same noise.
Yeah.
So with the same noise, if one initial data is bigger than the other initial data, then we have the comparison principle, right?
Yeah.
That's why, yeah.
I see, I understand.
Okay, so now we look at this delta. So this one is just subtract this one. Okay, say u minus v, this one minus this one. And here is two independent white noises. So we can replace, you can just compute the quadratic variation, and then we can replace this one is another space-time white noise. We get this equation. Okay, and the key is now we look at the, just like for parabolic Anderson model, we look at the total mass. So we integrate this one with respect to x. Okay, so this is non-negative. And then once we look at the quadratic variation, okay, we can obtain this from the previous slide. And this is a positive, so we can forget about this term. And u is greater than v, so we can take the infimum of this v square. And from here to here, it's just a computation. Okay, you can just compute right away, then you can get this. And from the second to third, here we use some stopping times to get that u and v are close to the initial data. Okay, somehow we can control those stopping times. Then there is some constant c which depends on u0 and v0. And then we'll see we can get the quadratic variation is like this way. So dx, the t is like xt. So if I think about this equation, the Feller diffusion, so the quadratic variation is exactly equal to yt, right? In this case, I mean, it is well known that you can prove that yt hits 0 in a finite time. So using kind of this result, we can actually get that. So there exists some time t, which depends on the initial data, delta, such that we have the positive, we have the complete coupling with a positive probability. So once x is 0, okay, this is non-negative, then we have to have u and v should be the same thing, since they are basically continuous. Okay, so but this one is for the case where U0 is greater than V0. So if U and V are not comparable, then we introduce another space-time noise, and then take the maximum of this U0 and V0. And we use the pairwise coupling between U and W, and U and W and V. Since W is a maximum, we have a complete coupling here and complete coupling here, so that we can have a complete coupling between U and V. And if we use U and V0 are not close enough, then we can wait until they are close to each other. This can be done from the following proposition. So the last argument is that, so once U0 here is V0, we wait for some time so that they are close to each other. And from this time, we use this pairwise, the anchored monotone coupling to see the complete coupling. If they don't couple, by time this T delta, and then we just wait another time that they are close to each other by using the strong Markov property. But then we also wait for the complete coupling, and there's a positive probability of a complete coupling. But these are basically independent. So we have many independent things with a positive probability, then almost surely there will be complete coupling. So this is the argument. Okay, so thank you very much for your attention.
Thank you, Kunwoo. Does anyone have any questions for Kunwoo? Okay. Yeah, so very, very nice talk, Kunwoo. Let's, so is there any way to, so these are the most, these are the best conditions on F. So I mean, maybe a bit more, can you give some explanation of how you came up with these conditions for F? I mean, where is it that you really use that?
So the one thing is, so to get this kind of compared to random walk, I mean, since when U is small, so here this term, because of this term, we can control that. We can control the intermittency basically, and then with this term, we can control the noise part. So if lambda is small, if lambda is really small, then this one is a dominating term.
Right.
Yeah, so we can get the, whenever solution is small, it goes. So if you think about the, for Markov chain, if we the Markov chain is irreducible and recurrent, then we have a unique invariant measure, right? A periodic, okay. But so here is basically like this: the solution U is goes up and down, but because of this the minus U square, it doesn't goes up. I mean much. And also because of this U, it goes really down, it doesn't go down below.
Yeah.
And if lambda is small, I mean, it can take really the drift wins against the noise term. So this is the idea that we have this kind of drift, like a U minus F of U.
So you must, so it must, F of 0 must be 0, and also
Yes.
F of X should grow faster than X when X is large, basically.
Yes, so when X is small, when U is small, we want this one is dominating term. When U is large, we want this one is a dominating term.
Right.
Yes. Yeah.
I see. So there should be some drift towards.
Yes.
Yeah. But yeah, it's very interesting to see this the phase transition of lambda.
Yeah, thank you.
I had one question.
And yeah,
in this lemma, so if lambda is little large, this whole thing will sort of collapse. Is it? Like, if lambda is larger, what happens?
Yeah, if lambda is large, then we really cannot control the noise. I mean, you really so yeah, then we may not have this one.
Interesting.
So are you saying that if lambda is large, the drift really has no effect on the random walk, basically?
Why?
Yes, and let me show you the method. So here is, in fact, also I want to say that lambda 0, we don't know what lambda 0 and lambda 1, I mean, we don't know actually what will happen in between. And because the reason is there's no comparison principle like Matthew and Davar and Carl has. So here, this one really depends on this lambda 0, and because we want to control that this one doesn't move much compared to the drift term. So the lambda 0 actually also depends on this. If it's instead of like a u or like 3u, then lambda also depends on like 3. Yeah, I mean to get the many invariant measures.
Kunwoo, is it not true that if you think of it as exponential martingale, I think that you mentioned it earlier to us, right? It's a bit like the exponential martingale, right?
The first one is exponential martingale.
But even for the second one, behaves probably a bit like that. The reason why you get for large lambda and for small lambda, you get different kind of behaviors, right?
Yes, for large lambda, so if lambda is large enough, then f of u minus f of u is a non-negative function. So by comparison principle, we can get rid of this one like here.
Yeah.
And this is like a e to the some constant times t, right? I mean this drift. So if lambda is large enough, then this one exponential martingale is like e to the minus lambda square times t.
Yeah.
Over 2. So that's why this one wins against the positive drift term.
So essentially, it's because in some sense the stochastic integral is essentially E2, and you get the E2 correction.
Yeah, E2 correction, yes, right. And it's basically the exponential martingale, more or less, yes.
Yeah.
Okay, if there are no other questions, then let's